So let's finish today's lecture. Today's lecture was interrupted by a fire alarm for those of you who weren't in class today. But I did want to spend the rest of the lecture sharing an animation with you that might help make some sense of the convolution process. So if you'll direct your attention to figure 1, which is on the left side of the screen, you'll see two signals, x of t and h of t, and my goal is to convolve them. So you can see that x of t is as a constant that stretches from t equals 0 to 4, and h of t is a constant that extends from t equals negative 1 to 1. So on the right, what you're looking at is essentially an animation of what we drew in class today, and it'll kind of help make the case for why we saw what we saw. So the first plot, the red curve, is x of tau. Tau is what I'm using for my dummy variable in this exercise. And you can see that x of t and x of tau are identical. The next thing you see is the yellow trace. The yellow trace is h of t minus tau. And h of t, to get from h of t to h of t minus tau, again, to follow the steps from class today, the first thing we do is we take h of t and we flip it across the y-axis. Now in this case, because h of t is symmetric across the y-axis to start with, flipping it doesn't change it. And the next thing we do is we shift it by t units, where t is some constant that we're going to move around. So the rule is always that whatever was at t equals 0 before the flip and shift just becomes t. So if you look at my flip and shift over here, the edge of h of t minus tau is 1 unit to the right of t, so that's t plus 1. And the trailing edge is will be at 1 unit to the left of t, so that'll be t minus 1, and that's off the screen right now, which is why you don't see it. Right now, to start things off, I'm using t equals negative 4, so this is the middle of h of t minus tau. That is at negative 4, and the rest of it's off the screen. The purple trace is the product of x of tau and h of t minus tau. And as you can see, it's 0 for all time. Technically, that's 0 for all tau. And when we integrate it, we get 0. And that's what you're looking at in the green trace. Okay. Now what I'm going to do is I'm going to use the slider to start incrementing my constant t. So let me slide it up a bit. And you can see now that for this particular value here, let me slide it over until t equals negative 2. So now you can see that t, which remember 0 always maps to t, so t is at negative 2. The leading edge is 1 unit ahead, t plus 1, and the trailing edge is 1 unit behind, t minus 1. And there's still no overlap between x of tau and h of t minus tau. So I'm going to keep sliding it over, and already we can understand that the overlap will end when t plus 1, the leading edge, the overlap will start when the leading edge, t plus 1, lines up with 0. And that will occur when t equals negative 1. If t equals negative 1, then the leading edge will be 1 unit more than that, which is 0, and that's where the overlap will start. Okay, and now we see that that's actually happened. So t is now greater than negative 1. And so now there is a teensy-weensy little overlap between the two traces. So the purple signal is what the product of those two traces look like. And then finally, I'm going to integrate that. So you can see there's a little bit of blue here. That's the area under the curve. And whatever the area under the curve is, that's my y of t. Okay? And you can see here that t is negative 0.9 in this case. So therefore, whatever the area under the curve is corresponds to t equals minus 0.9. And that's why you see the line over here at t equals minus 0.9. All right, now, as I keep shifting to the right, there's more and more overlap between the two signals. And as there's more and more overlap, you can see the purple signal getting wider, therefore there's more stuff to integrate. And in this case, it's increasing in a linear fashion. Okay? Now, once the yellow signal is all the way under the red signal, which happens when t minus 1 arrives at 0, or in other words, when t equals 1, now the integral doesn't change anymore, right? The area under the purple signal is constant, and that happens starting at t equals 1. And that will continue until the leading edge of h of t minus tau lines up with the leading edge of x of tau. So if you imagine when t plus 1 lines up with 4, that'll happen when t equals 3. And therefore, you can expect that when t equals 3, now there's going to start to become less and less stuff to integrate, and therefore y of t will go down until there's nothing left to integrate. Okay? And so that is my attempt to explain with a graphical method how flip and shift works to solve convolution. So I'll post this code and you should play around with it. All you have to do is run the M file that I post, and hopefully that should help make a little sense of the convolution process.